After discussing the digital to analog converters, let us now discuss ADC. ADCs are crucial components in modern signal processing and electronics. They act as the bridge between the analog and digital worlds by converting real-world analog signals into digital data for processing, storage, and communication. The block diagram of a general ADC highlights the key stages involved in converting an analog signal to a digital output. An anti-aliasing filter, that is pre-filter, is essential to prevent higher frequency signals from aliasing into the baseband of the ADC. In many cases, this filter is realized through the band-limiting properties of the ADC itself. The filtered signal is then passed to a sample and hold circuit, which ensures the input analog signal remains constant during the conversion process. The time taken for this conversion is referred to as the conversion time of the ADC. The conversion process involves a quantization step, which segments the reference signal into subranges, typically 2 to the power n subranges, where n represents the number of bits in the digital output code. The quantization step identifies the subrange corresponding to the sampled analog input. This subrange information is used by the digital processor to generate the corresponding digital output code. The frequency response of the ADC is crucial to understand. When an analog signal with a bandwidth Fb is sampled at a frequency Fs, the frequency spectrum of the input signal can be aliased if Fb exceeds 0.5 Fs. This aliasing results in overlapping spectra, making it impossible to recover the original signal. The Nyquist theorem states that the sampling frequency must be at least twice the signal bandwidth, that is, Fs greater than or equal to 2 multiplied Fb to avoid aliasing. To prevent this, a pre-filter or anti-aliasing filter is used to limit the signal's bandwidth to below 0.5 multiplied Fs. If Fb is too high relative to Fs, spectra will overlap, and recovery of the original signal becomes impossible. This is avoided by ensuring Fb is below 0.5 multiplied Fs. But implementing a sharp cutoff filter to achieve this is complex. ADCs that follow the Nyquist criterion are called Nyquist ADCs. For cases where Fb is much lower than 0.5 multiplied Fs, oversampling ADCs are used. An analog-to-digital converter, or ADC, bridges the gap between the analog world and digital systems by converting continuous signals into discrete digital codes. Point 1. Input and output. The input to an ADC is an analog signal, most commonly an analog voltage. On the other hand, the output is a digital code, which represents the analog input in a digital format. Point 2. Analog input range. The analog input can take any value within a specific range, typically between 2000 and V, where V is the reference voltage of the ADC. However, the digital output is restricted to specific, fixed amplitudes, which correspond to quantized levels. Point 3. Digital codes. Various digital codes are used in ADCs to represent the analog input. Some popular codes include binary, the most common format, widely used in almost all ADCs. Thermometer code, often used in certain high-speed applications. Gray code helps minimize errors during transitions. 2's complement, useful for handling sign numbers. Point 4. Most widely used code. Among these, the binary code is the most widely used because of its simplicity and compatibility with digital systems. ADCs play a critical role in translating continuous analog signals into discrete digital formats, making them essential for a wide range of digital processing applications. The static characterization of an ADC is illustrated by the input-output characteristic for a 3-bit ADC shown in Fig. In this plot, the input values are shifted so that the ideal step changes occur at values of 0.5 times LSB, least significant bit, for each bit level. Specifically, these step changes occur at input values of 0.5 times LSB times 2i1, where I varies from 1 to n for an n-bit ADC. Beneath this input-output characteristic, The quantization noise is plotted as a function of the input voltage. Quantization noise represents the difference between the ideal ADC characteristic with infinite resolution and the actual 3-bit characteristic. The quantization noise is typically within the range of plus minus 0.5 times LSB, which reflects the error introduced by the finite resolution of the ADC. This noise occurs because the ADC can only approximate the input signal, and the difference between the ideal continuous signal and the discrete output is quantized. We'll discuss some important characteristics and definitions that help us evaluate the performance of analog-to-digital converters or ADCs. Point 1. Dynamic metrics. First, the definitions of dynamic range, signal-to-noise ratio, SNR, and effective number of bits, NOB, are consistent with those used for DACs. However, in the case of ADCs, these metrics are referenced to the digital output word, reflecting the digital nature of their output. Point 2. Resolution of the ADC. The resolution of an ADC is crucial as it determines the smallest analog input change that can be distinguished. It's typically expressed in two ways. Percent of full scale, FS, representing the smallest change as a percentage of the total range. Number of bits, N, indicating the total possible output states, which equals to the power N. Point 3. Static performance characteristics. Next, we have the static performance characteristics that define the accuracy of the ADC. Offset error. This is the deviation from the expected output value at zero input. Gain error represents the difference in slope between the actual and ideal transfer functions. Think of it as how the slope of the ideal line shifts either above or below a value of 1. Integral nonlinearity. INL measures how much the ADC's transfer function deviates from a perfectly straight line. Differential nonlinearity, DNL, quantifies how much each step in the ADC's output deviates from the ideal step size. These characteristics, both dynamic and static, are essential for understanding the performance and accuracy of ADCs in various applications. Together, they provide a comprehensive picture of how well an ADC translates analog signals into digital data. The dynamic characteristics of analog-to-digital converters and the key factors that influence their performance. Point 1. Dependence on components. Similar to digital-to-analog converters, the dynamic performance of ADCs is affected by the same factors, such as parasitic capacitance and operational amplifiers, op-amps. These elements introduce limitations on speed and accuracy, especially at high frequencies. Point 2. Use of comparators. Another critical component in ADCs is the comparator, which is present in all ADC architectures. Its role is to compare the analog input signal against a reference voltage and decide whether the input is above or below that reference. This decision forms the basis for generating the corresponding digital output. Point 3. Importance of comparators. The accuracy and speed of the comparator directly impact the overall performance of the ADC. As a result, optimizing comparator design is a key focus area in ADC development. These dynamic characteristics, including the dependence on components and the pivotal role of comparators, are fundamental to understanding the operation and limitations of ADCs. Thanks.